Good day, everyone. Good day. This is Science Clinic Online Extra Lessons with your tutor, Mudau L. So, in our previous lesson, we learned about the normal force, and we also look at the cases where the object is on the horizontal plane. So, we define those cases. Today, our focus will be on an inclined plane. How do we define normal on an inclined plane? So if you go to your exam guideline, you will read this statement which says that for inclined planes, the only forces perpendicular to the plane is the component of the weight and the normal force. All other forces should be parallel to the plane. So this is what is written in your exam guideline. Now, I want us to look at some cases. Remember the definition of a normal force is the force or the component of a force which a surface exerts on an object in contact with it and which is perpendicular to the surface. It's perpendicular to the surface. Keyword must be in contact and it acts perpendicular to the surface. Now, let us look at this case number one. Normal force on an inclined plane. Normal force on an inclined plane. So let us have this as our first case. This object lies on this rough inclined plane. Now, I want us to draw the free body diagram showing all forces acting on this block. The first force is going to be weight. I will use Fg this time around. In our previous lesson, we were using W. So it's all the same. And we have this force which acts perpendicularly to the surface, which is called the normal force. And this object, the possibility is that it can only go down. It can be pulled by the weight component. So this one is going to be our friction. Remember, when we do this, we must also label our forces. We must also label our forces and normal, Fk, friction, Fg, weight. Now, I want to show you the component of the weight, component of Fg. We have this component, which is always in the opposite direction with the normal force on an inclined plane. It's called Fg perpendicular. And we also have this component. This is Fg parallel. This Fg parallel. It always points down the slope. So our angle theta is going to be here. Now, if you see from this theta, you can see that Fg perpendicular is going to be defined by Fg. We are resolving Fg into its components. So by Fg, because it's adjacent, is going to be cos of theta. And this is mg cos of theta. But Fg parallel is going to be defined by Fg is opposite, then it's going to be sine of theta. This is mg sine of theta. Now let us look at our normal force. Now, how do we define our normal force for this case? If you check, normal force is in opposite of Fg perpendicular, and these two forces are at equilibrium. They are at equilibrium. Therefore, normal force is equals to Fg perpendicular. In other words, we are saying that this is mg cos of theta. This mg cos of theta. This is mg cos of theta. I hope that is clear. I hope that is clear. Now, I want us to move to case number 2. Now, let me change the diagram and draw it in this fashion so that some of the learners, they just cram this. So I don't want you guys to cram. I want you guys to understand this our theta. Then we have our block here. And we have the applied force here. So what we are going to do here, and the surface is rough. If you are not told that the surface is smooth, then it's rough. You don't have to worry about that. So they don't even have to show that the surface is rough. So they must only tell you that this surface is smooth. This surface is smooth. Hence, let us draw the free body diagram for this case. So this is what we're going to have. The first force, Fg. Second force, normal. It always acts perpendicular to the surface. And this force is the applied force. So down, going down, we're going to have this Fk. This is Fk. So in our previous example, we said is Fk. No, it's not Fk. It can only be Fk if it's moving. So this one, let's just assume it's not moving. We'll just say it's Fs. It's Fs. Fk, that is the kinetic frictional force. So I will show you in our next lesson. Now, here we have Fk because it's moving. Now, this F, it has components. Fg, it has components. So there is this component. This is Fg perpendicular. So our theta is here. And we also have this component, Fg parallel. So this one, it acts parallel to the surface, always acts parallel to the surface. Now, as you can see, we know how to define the components of weight. So normal force here is going to be defined by Fg perpendicular. So it's the same as in our previous case. Now this is mg cos of theta, mg cos of theta. So it's the same as the previous one because the F applied is not at an angle. So now let us go to this special case, case number 3. This one is a special case. Then we go and look at some example. Special case for special people. So the examiner loved this case. This is theta 1 and theta 2. So we are having this case. So the plane is rough. The plane is rough. I want us to draw the free body diagram. So let us draw the free body diagram. The first force, of course, is going to be Fg. The second force, it must be normal. This is the normal. And we have this other force, which is applied. So for applied, let me first do this. Then this is the surface. Then our applied is going to be at an angle in this fashion. This is our applied. Then we have our friction. So since it's moving, we're going to use Fk. We're going to use Fk. So this is the free body diagram. This is the free body diagram for case number 3. This is the free body diagram for case number 3. Now, I want us to look at the components of the weight. Components of the weight. We have this component here, FG perpendicular. We have this component here, FG parallel. So since that force, which is our F applied, is at an angle, it also has what? Components. Therefore, it has this component, which is called Fx, and also this component, which is called Fy. So by the look of things, you can see that now the normal force, plus Fy, this will give us Fg perpendicular. So I hope you can see the difference. You can see the difference with the previous two cases. Now, normal force in this case is defined as Fg perpendicular minus Fy. So Fg perpendicular, we know that is mg cos of theta, and it's going to be theta 1 for this case. Here is going to be F psi of theta 2. So this is how we are going to define our normal for this case. This is how we're going to define our normal for this case. So please, you must pay attention. You must pay attention to these cases. Before you can attempt a question, just look at the diagram and see the possible forces. So you can be able to see how you can define the normal force, or you can define any other force that is acting on an object. Now, I want us to go straight to examples. I have 3 examples that I want us to look at. I have 3 examples that I want us to look at. Example number 1. Here is the first example. So it says that a block of mass 5 kg is placed on a rough plane inclined at 35 degrees to the horizontal. Draw a free body diagram showing all forces acting on the block. That is the first question. Second question, it says that calculate the normal force. Calculate the normal force acting on the block. Acting on the block. Calculate the normal force acting on the block. Okay, guys, let us minimize our screen so that we can have a space to write. Now, the first question, it says that draw a free body diagram. Okay, let me first read the statement. You must always read the statement before you attempt the question so that you can understand what is the scenario all about. Now, it says that a block of mass 5 kg is placed on a rough plane inclined at 35 degrees to the horizontal. Draw a free body diagram showing all forces acting on the block. Let us draw the free body diagram up here, showing all forces acting on the block. 1.1, a dot, this is normal force, this is Fg, and so this block was just placed on a rough, meaning that we're going to have this force, which is the, let me have static frictional instead of kinetic, since it's not moving. So these are the forces acting on the block. These are the forces acting on the block. Now, let us calculate the normal force. So what must come in your mind is that this is case number one. So for case number one, normal force is equals to Fg perpendicular. And this is mg cos of theta. And what is the mass is 5 g 9,8 cos of 35. Cos of 35. Now let us press our calculator here. 5 multiplied by 9,8 cos of 35. Cos of 35. So it's going to be 40, 40,14. 40,14 newtons. So this is our normal force for this problem. Now I want us to go and look at problem number 2. Problem number 2. Here's the problem number 2. We are done with the first one. So number 2, let us first read, then we will write later. So it says that a 20 kg block is pulled across the rough inclined plane, which forms an angle of 30 degrees with the horizontal, with a force of 215 newtons. So draw a free body diagram and force diagram showing all forces acting on the block. Second question, calculate the normal force acting on the block. Now, let us have space to write. Then we're going to draw the free body diagram. So what must come in our mind is that this is case number 2. Normal force is equal to Fg perpendicular. So with the drawing, let us start with the free body, then we will do the force diagram. Free body, this side, force diagram. With the free body, this is what we're going to have. Of course, let us start with the Fg. And here we're going to have our normal force. And here we're going to have our applied force. And here we're going to have our Fk. So then we are done. Let us draw the same forces, but we can use a box or a circle. Let me use a circle today. This one, we have normal, we have applied, we have Fg, we have Fk. So this one is the force diagram, or we can just use a box. We can just use a box. Okay. Now let us proceed to question 2.2. 2.2, it says calculate the normal force. I said that for this case, normal force is also equal to Fg perpendicular, which is mg cos of theta. So m is 20 multiplied by 9,8 cos of theta, which is 30. Now let us do our calculations here. So it's 20 multiplied by 9,8 because we are assuming that we are on Earth. Cos of 30, then this is 169,74 newtons. 169,74 newtons. So this is how we can calculate normal force on an inclined plane. So there are other techniques that we will do on how we calculate normal force. Maybe when we are given friction and the coefficient of friction, etc., etc. Then let us proceed to the last example. Let us proceed to the last example. The last example for today, example number 3. Example number 3. is related to case number 3. So it says that a man is pulling a 60 Newton box up an inclined frictionless plate with the force F equals to 25 Newtons, whose direction makes an angle of 30 degrees with inclined plane. The inclined plane makes an angle of 20 degrees with the horizontal. So the first question is just to draw the free body diagram. The second question is to calculate the normal force. So this one is related to case number 3. It's related to case number 3. So let us get a space where we can write and solve this one. 3.1, we have to draw the free body diagram. Remember, when you draw the free body diagram, you must draw a labeled one. So we have this force. Oh, sorry, let me erase this, which is called Fg. And here we're going to have normal. So here we're going to have this F applied. And since it's frictionless, we are not going to have friction because we are told that the incline is frictionless. So these are the forces acting on the block. But we know that F applied, it has components, and Fg, it also has components. So now let us calculate the normal force, 3.2. Let us calculate the normal force, 3.2. It says that normal force plus Fy, this is Fg perpendicular. This is Fg perpendicular. So normal force is equals to, you can refer to case number 3. Minus Fy, and this is mg cos of theta 1 and minus F sine of theta 2. M is the mass of this object. So we are given the weight of the object. So what we must do is to first calculate the mass of the object. Let us calculate the mass of the object, or even if you don't want to calculate the mass of the object, you know that weight is mg. Hence, this is what you're going to do. Where there is mg, you are going to substitute by what? By 60 newtons to avoid recalculating the mass and do the same thing. So that one, it will be a long dry. So let us take the weight because mg is the weight, right? Now, cos of angle theta 1 is 20 minus F is equal to 25. Sine of theta 2, of course, is 30. Theta 2 is 30. Then we press our calculator and find the answer. Let us press our calculator and find the answer for this one. It says that 60 60 cos of 20 minus what? 25 sine of 30. And the answer is 43,88 newtons. 43,88 newtons is the normal force for this case. So if you have any question, you can contact us through the number on our channel or email us, then we will get back to you. Or you can just leave the comment on the comment section, then we'll get back to you. Thank you for watching. I hope you have learned a lot. See you next time.